Hey, Jan,
Hello.
you were all by yourself, feeling
Yes.
lonely. Here, people are starting to show up. You see, just as they were waiting for me. How's everything going?
uh, let's say quite well, but the numbers of the uh, COVID cases are rapidly increasing.
Yeah, I heard that things are not looking as nice as they should at this point. What's the general feel about the booster shots in Czech?
Not sure. I don't know. It's not that widely discussed. We are still uh, kind of campaign for increasing the number of vaccinated people, and actually it seems that the most of the cases are in the range of 12 to 20.
Mhm. Are teenagers getting vaccinated, or is it mostly in the older range?
So the vaccination is this is mostly the most.
Recording. Okay, so thank you everyone for joining in. Whoever can open their camera, I think it's nicer for everyone to mimic the live sessions. So COVID is bad in the sense that we can't personally meet, but it's great in the sense that uh, we can ask people like Jan to join the seminar, and we can get a broader range of uh, people presenting in the seminar. I'm super excited to introduce Jan. Jan is in the past 2 years also not only a colleague but also a collaborator. So that's a fun thing on my end. And I think what's really cool about Jan's work is the breadth. So today we're going to hear about curvature-constrained multi-goal trajectory planning, and probably most of the things that we're going to see is in simulation and with some theory behind them. And the other facet, or to the other end of the spectrum, Jan has also participated in the recent DARPA Subterranean Challenge, and in one of the instances, was it second or first place? Yeah.
Was for the finals we have been second in the simulation league, in the virtual league.
Which, if you're not aware of the challenge, this is super competitive, systems-oriented robotics challenge. So it requires to be a full stack roboticist, and which shows Jan's both breadth and depth as a roboticist. With that, I'm super excited to have Jan here, and Jan, the stage or the mouse is yours.
Yeah, thank you for a very kind introduction. My first slide, that's the broad teaser what we are doing in my lab. It's motivated by robotic information gathering, and as a dimension, we work with real robots as well as the algorithm part. And we recently participate also in not only virtual track but also in the system track, and you can see how a couple of our robots in this photos. So what is the idea behind our research, and that is also part of the lecture, is that we really aim to provide good solutions by two means. The first is the theoretical guarantees, and of course, if you think about deployment of the algorithms in real scenarios, usually in unknown environment, a priori unknown environment, you need to do the decisions in situ, which also has the requirements on the fast computations. And for the today talk, I prepare the overview of multi-goal planning with curvature-constrained trajectories, which is essentially motivated mostly by area vehicles. And in the lecture, I would like to capture some of those very specific results for Dubin's vehicle model and extend it to a couple of interesting scenarios. And in the end of the talk, I will provide you some future extensions to variable speed trajectories and 3D trajectories. So what is the motivation? It's arising from area vehicles where we have naturally curvature-constrained trajectories, especially for fixed-wing vehicles. That's for sure. The vehicle needs some speed to be in the air, and the curvature is limited by some minimal turning radius, which is kind of related to the velocity of the vehicle. But curvature-constrained trajectories are also suitable for like these multi-rotor drones, even that these drones can move in arbitrary direction, but it is still beneficial to have some smooth trajectories. And if you like to deploy these vehicles in the missions, in data collection missions for us, where the drone visits some of the locations and take a snapshot or even pick up something or deliver something, it's still a kind of multi-goal planning, because we are not interested only in a point-to-point planning, but in some more complex scenarios. And there are actually two types of problems. The first is how to visit all of the locations, which naturally has some traveling salesman problem, some routing problem. Or you explicitly address the limited endurance of the vehicles. That means that you cannot fly for visiting all the locations, but you need to prefer some of them. And that's kind of limited travel budget and maximizing the profit. And in the rest of the talk, I will concentrate on these routing problems, especially related to this traveling salesman problem. But what are the real let's say, challenges that we need to address? At the left image, what you can see is a trajectory that is like two types of trajectory. One is curvature constraint, and that's the blue one, and the one is in the red is for straight line segments. And what you can see probably here, is that even that we can eventually plan using the straight line segments, when we execute the trajectory or the path that the optimal trajectory follower still needs to somehow, and it is actually visible here, to consider the dynamic of the vehicle. And we will, for example, in this case, and all those is probably seen here, we actually cut the corners, and we really require to visit that location precisely, we will actually fail in that. So that's the reason why we need the curvature constraint trajectories in even for multi-rotor drones. And on the other image here, what you can see is that if you have this set of locations, kind of TSP, and we will consider a sequence found by like Euclidean solution of the TSP, then depending on the turning radius, the sequence is no longer optimal, and we need to directly address the minimum turning radius. And one more motivation is that you actually don't need to visit the location exactly. And in many cases, it is just sufficient to visit some neighborhood, some region, especially if you have surveillance missions. You don't have like small field of view, you usually have large field of view, and it is sufficient to reach the object of interest or point of interest within some vicinity. And what is the benefit for us if we are able to exploit this sensing range or distance? Then we can save the travel cost. So these are the motivation why we need the curvature constrained multi-goal trajectories. And of course, we can be satisfied with some of the solution, but we really like to have some quality guarantees, some quality estimates of our solutions. And that's the whole part of most of the part of this lecture is how we can actually estimate the solution quality. So just some preliminary, what is the Dubin's vehicle, and we show the results mostly for this kind of very simple model, but still sufficiently realistic for many of our cases. So Dubin's vehicle is considered to move at a constant forward velocity and has some limited minimal turning radius. And this turning radius is mostly when you are turning, you can turn at some velocity. Of course, that some future generalization exists, but what is the nice property of this model that regarding the optimal connections of two configurations, we have closed form solution that exists for many years. And what you can also find that this has been established by Lester Dubins in 1957, but also the problem has been studied by Markov, so you can find Markov-Dubins paths in the literature. So what this actually provides us that if we have two locations, but with a prescribed heading angle of the vehicle, because we need to leave the location at some azimuth and also reach some location, then we can establish optimal paths. And because we have constant velocity, that's also like optimal trajectory in closed form solution. And we can identify there are two types of maneuvers. One is called CCC and one is called CSC. And it's because in this maneuvers, we have three types of segments or three segments. And we need to make the, for example, here left turn, right turn and left turn, or there can be some straight line segment. And what maybe you can immediately see is that once these locations are far enough, then there should be this straight line segment. And depending on the angles we have, the headings of the vehicle at the locations, and once the locations are close to each other, then we have this CCC maneuver, and that's actually kind of troublesome for many of our, let's say, solution quality guarantees. So in the end, we can have 6 types of maneuvers. But what is the main trouble for our problem, multi-goal planning problem, is that we don't have these headings. So we have just a bunch of points without the headings, and we need to establish them. And what you can find in the literature for sequencing problem is the traveling-salesman problem. Now we have the Dubins, so we have Dubins traveling-salesman problem. And if we like to visit not a pure region, but some region, like disk region, then we will have the neighborhoods.
Jan.
Yeah.
There's been questions from the audience. Do you prefer questions while you talk, or do you prefer to talk in questions at the end? You're the boss here.
That's what is usual for this kind of seminars. So
we're Israeli, so we usually interrupt.
Okay, so let's interrupt me. No problem.
Okay, so I actually have a question.
Yeah.
But Kirill was polite enough to ask if he can interrupt. So let's let Kirill interrupt first.
Okay.
So go ahead with the question.
Kirill, we can't hear you. You're not even good at interrupting.
Pardon?
Erez, maybe while Kirill is getting his mic ready.
So I'll ask my question. So what happens if we're talking about, let's say, an airplane or something, so in 3D?
I will go that in very light.
Okay, thanks.
Just provide some preliminaries, and I will discuss that at the end of the talk. Okay. What is other problem of the problem is if you have the limited travel budget and you maximize the profit by visiting the most rewarding locations, that can be found in the literature as orienteering problem. I will not tackle the orienteering problem too much, but provide you some foundations how you can address that. So regarding this relatively straightforward model with optimal paths for these configurations that we have the headings, is that I already tried to mention is that this is the troublesome, because if we have the locations, and if you imagine that that we have the situation like here, and now we will decrease the distance between the configurations. Naturally, the length of the optimal path is shortening, but at some point, depending on the heading angles, we need to make this CCC maneuver, which prolongs that. So, which means that the length of the optimal Dubin's maneuver, depending on the heading angle, is not monotone with the distance of the configurations, and it's piecewise continuous. So that's somehow shown here in this animation. So we can see that we have the heading angle of the one location at the X, and on the Y, the other heading angle, and we increase the distance between the locations. And what you can see here is the length of the optimal maneuvers. And here is a kind of distribution of the particular maneuver type. And that's the most troublesome thing to actually guarantee the solution quality. What is the Dubin's traveling salesman problem? I would like to just highlight that it's a combination of the combinatorial optimization. I assume that all of you know what is the TSP. And what we need is establishing the headings. So for each location, we need to figure out what is the best heading regarding the sequence. So it's sequence dependent. And it's kind of combination of the combinatorial and continuous optimization. And also in this cartoon, you can see that if we fix the sequence depending on the heading angle, which is depending on the turning radius, the heading angles, even that are found optimally, let's say, for this sequence, the whole solution is not of sufficient quality. And what are the general approaches to the traveling salesman problem or any kind of routing problem with Dubin's vehicle is basically two fundamental approaches. And one is that we have this trouble with combination of combinatorial optimization, TSP, and continuous optimization of finding the headings. So we can separate these problems, decoupled, find some sequence, for example, using Euclidean TSP solution, and then focus on the establishing the heading angles. That's the continuous and variables optimization. And from my perspective, this is an important part, and that's why we call the problem for a given sequence, finding the optimal heading angles, as a Dubin-Turing problem, because it's actually kind of evaluation of possible sequences. And we will discuss that in a few moments. Another approach is if you have trouble with the continuous domain, let's sample it and transform the Dubin's traveling salesman problem to some purely combinatorial variant of the TSP, and that's generalized TSP. If we take a look to the literature and try to somehow classify what are the existing approaches, you can find a huge set of heuristic approaches. There is actually one approach that provides some approximation algorithm, but the bound is unpractically high. There are also the sampling-based approaches that are resolution complete. Not surprising that the computation requirements are increasing with the number of samples. And then I would also highlight the decoupled approaches. So now let's assume that we have some sequence, we find a good sequence. And you can find an optimal solution based on convex optimization, but only for the case that the locations in the sequence are far enough. And there are two important solutions regarding some lower bounds that has been introduced by Gupta in 2016. And that's, in my opinion, change the way how we can assess the quality of the solution. And that's is covered in the rest of the talk. So let's start with the Dubin's Turing problem. Now we have the sequence of visits. So we have the locations. So we have this sequence 1, 2, 3. And the problem is to find the optimal headings. So it's an variable optimization problem. Can find the headings arbitrarily selected from interval 0 to 2p. And we can consider this, okay, we can found sequences in many or any kind of routing problem with Dubin's vehicle. So if we are able to solve this problem nicely in a computational efficient way and high quality solutions, then we can enable the solution of other Dubin's routing problems. That was our idea, or it is the idea behind. How we can address that? Again, you have continuous domains, so let's sample them. And because we have prescribed sequence of visits, so we can create this search graph, and using dynamic programming, we can find optimal solution for a given sampling. In polynomial time, we can see it's linear with n, and depending if we have closed or open road, then it's k cubic or k square. So that's a relatively straightforward approach, but still, how we can sample that? So we can sample the heading intervals uniformly, like this one, or we can do it more smartly, like in this case, we call it informed sampling. And what you can see here is that we probably here use more samples, which is more demanding. Here we use less samples, which is faster. And regarding the solution quality, that's this number, we are better here. And what is really important part that we also have the lower bound estimate on the solution, optimal solution value. And for this case, this is the red line. It's a kind of worse solution than in this case that we see that it's almost close to the lower bound. And the question is how we can establish the lower bound. And that's because we have this Dubin's interval problem. And let me introduce that. Dubin's interval problem can be considered as a generalization of this Dubin's planning. So we have one location, we have second location, but instead of defined single like leaving angle or single angle of arrive to the destination point, we have prescribed heading intervals. So we have some interval within which we assume that the vehicle can leave and arrive. And the problem, Dubin's interval problem, is what is the cost of the optimal Dubin's maneuver, starting at one location, reaching the another location under the constraint that the leaving angle is within the interval and arriving angle is within the given interval. And that solution can be found analytically. And as one of my students at the lecture asked me, what does it mean analytically? Actually, it's not closed form expression, like single expression. It's a couple of expressions, and you need to evaluate and then choose the one that satisfies the constraint and is the shortest one. But generally, we have analytical solution to that, and it is very useful because we can use that for establishing tight lower bound of our Dubin's Turing problem. Why? Because we will use the same technique of the sampling, but instead of heading interval headings values, we will use the heading intervals. We will use the same methodology, dynamic programming in the search graph, find the optimal solution, but not using the solution of the Dubin's path, but Dubin's interval problem. What is the limitation of this, or why we are calling the lower bound? It is because we have the interval, and the arriving interval is within this interval. The arriving angle is within this interval, but leaving angle can be a different, but still within the interval. So it is actually not a feasible solution for like connecting this. This is the solution of the dip, and this is the solution of the dip. The multi-goal trajectory constructed from this Dubin's interval problems, or solution of the Dubin's interval problem, is not a feasible solution because here we abruptly change the orientation of the vehicle. But we can establish using this some quality estimate, and we know that the lower bound is tight, and using this sampling motivated by this Dubin's interval problem on the lower bound, we can achieve solution quality that is quite close to this lower bound that from practical point of view can be considered optimal. But how we can do that, how we can sample, how we can utilize this lower bound. So the idea is quite straightforward. So we call it iterative refinement informed sampling, iris of headings, and you can imagine that we start with some rough division of the intervals, solve this lower bound solution, solve these Dubin's interval problems, and use these intervals from this lower bound and split them, and do that again. And how it can looks like. So we have this iterative for uniform sampling on the left and on this informed sampling on the right. So we start with the very same resolution, and we split here the lower bound and here the lower bound, and we can iterate it up to some point. Hopefully one more. Okay. And what we can see here that using this lower bound for splitting the intervals in more informed way provide us solution, which is actually the same as the solution using the uniform sampling, but we use less samples in total. And even though that you can argue that we don't need to do it iteratively, using uniform sampling, we can still save 1.6 seconds, and which is by orders of magnitude more demanding than using this informed sampling. So
can I ask a question?
Sure.
So okay, thank you. So you mentioned that you get the first solution very quickly, which is not surprising, right? Because any sequence of locations you pick, it gives you a valid solution, right?
Yes.
But what happens if you have constraints on possible sequences, or maybe an upper bound on the cost corresponding to battery or something like that?
So if you really need to address that, like the trajectory should be within some like time budget that you can, like usually multi-roton drones last for 20 minutes, half an hour. Then you need to address this problem as an orienteering problem, or it is the way how you can address that. But within this orienteering problem, you still need to evaluate the candidate. So basically, what is the orienteering problem? Let's put it in this way. So you have a bunch of locations, and you put some rewards to that.
Mm-hmm.
And you have some starting location, some ending location. This is the start, this is the end. And now what you really need is you cannot visit all of them, because for sure your budget is not enough. So you need to select the subset, what is reachable for you. And you will, if you have these rewards, then you can maximize the profit.
Right.
But to ensure that you still reach your budget, you still need to find, if you, for example, I will pick up by some strategy. Okay, this is the good candidates, and then what you need is to solve the problem that you will start here and visit these 3 locations. Maybe you can sketch using Euclidean distance that, okay, this is probably good sequence. And now you have the sequence, and you need to evaluate if your Dubin's vehicle will satisfy the limited travel budget. Right. Again, you need to solve actually this Dubin's Turing problem. But
yes,
it is within more, let's say, more complex combinatorial problem.
Okay. So I guess maybe the thing I'm trying to get at is whether the innovation here is in solving the Dubin's interval problem, or in quickly finding a feasible sequence.
Yes, the second one.
Okay.
So really the innovation here is that in a computational efficient way, we are able to find very high quality solutions for this Dubin's Turing problem And it is, in my opinion, essential because you can use it in any kind of routing problem with the Dubin's vehicle.
Okay.
And hopefully I will convince you in a few more slides.
Dr. Faigl, may I ask a question quickly?
Sure.
If I understand it correctly, with this orienteering problem, are you suggesting that we can solve it optimally in polynomial time, or did I understand it incorrectly?
That's not correct. The orienteering problem itself, without any Dubins, you can consider it as a combination of knapsack and TSP. So there are two NP-hard problems. And if you introduce Dubins vehicle into this problem, then you need to think that evaluation of the cost of any sequence, any routing subproblem within the orienting problem will be most likely more demanding than using some pre-compute distance cost metrics.
Okay, thank you.
I have a somewhat related follow-up question. I'm curious if you considered viewing this problem through the lens of TSP with neighborhoods, where it's a similar problem where instead of visiting just one location, you have several locations that represent the same location, and you can reach either one of those. And I know that for some settings of this problem, polynomial time approximation algorithms exist.
Actually, very good question, because we can consider these headings or possible headings as a neighborhood which has this 0 to 2p, right? So it is actually kind of TSPN, but because the cost depends on the actual maneuver, and if you remember that we have the CCC and CSC. And if we use this CCC, or we need to use this maneuver, that's kind of the difficulty, because we now enlarge or increase the length of the Dubin's path. So we treat it as a Dubin's traveling system with neighborhoods, but we didn't find any relation to the existing approximation schemas.
Thanks.
But I will take a look to the link you put to the chat. Thank you. So we have this solution of the Dubin's Turing problem, and we can go back to the traveling system problem. And I will provide you one more decoupled approach, just for showing what is the other approaches. And that's the alternating algorithm. And it's kind of one of the very first approach, the coupled approach to the Dubin's traveling system problem. And the idea is also very straightforward. And we have a bunch of locations how we can establish the headings. So we can use the even edges and connect that by straight line, which will force us what is the arrival and leaving angle, and then compute the optimal Dubin's path. So very naive, very computationally efficient, but the question is how good it is. And if you consider, okay, this is type of approaches that we fix the sequence, we use the sequence as a solution of the Euclidean TSP, and then we tune and find better solutions of the headings. Or we can use some evolutionary approach that also address and optimize the sequence. And we take a look what on some set of the instances, what is the actually solution quality. And what you can see in this plot, that actually it is not that bad. So this result suggests that if we are able to find high quality angles, high quality solution of the Dubin's string problem, maybe the Euclidean TSP is, in most cases, sufficient sequence. Of course, it's not optimal, but it is computationally efficient, like 10 seconds in comparing to 1 hour of memetic algorithm. And we can speculate that the memetic algorithm is not that smart, but still provide us that a good solution of this Dubin-Turing problem might provide us the benefit in evaluating multiple sequences. And we actually did it, and we try to exploit that. And that's the enabler. So because we are able to find very high quality solutions of this Dubin-Turing problem, then we can create instances and we can learn a surrogate model to quickly estimate the solution quality of any kind of sequence. There is one more issue, and that's we can learn the solution, for example, like that we will have two free sequences, free locations in the sequence. You can consider 5, 7, etc. And we need kind of generalize that. And we did it as like using this windowing and overlapping windowing. So we estimate the cost of the sequence as a sum of subsequences, or cost of the subsequences. We call this model windowing surrogate model, and take a look how it performs. So we use it, and we use very straightforward evolutionary algorithm for TSP, but with this pre-learned estimator of the Dubin-Turing problem. And this is the alternating algorithm. This is simple local iterative optimization. I will describe later. This is simulating and sampling-based methods, and we have this windowing schema here, and that's for 100 target locations. But what is probably not that directly visible, it also depends on the density of the location. So if these locations are far enough, the sequences are not that important, and we can use the Euclidean TSP as a good solution. That's why this is not that bad. But if we increase the number of target locations, then we can see that using this learned model provide us much more better, let's say, scalability. So that's, from my opinion, is so far best performing solution for this kind of Dubin-Turing assessment problem. Of course, it needs some initialization, but provide us the way how we can benefit from these theoretical results on lower bounds and tight lower bounds in let's say, evolutionary or genetic algorithms based solutions. But one of our future motivation is that in the real deployments, we don't need to visit the locations exactly. We may exploit some non-zero sensing range. And now the problem is actually kind of two neighborhoods. One neighborhood is from the headings, because each heading can be from 0 to 2p. And other neighborhood is that we can arbitrarily choose the location within these regions. But what we can do is that we can assume that the disk might be visited at the boundary, and we can actually encode this as angle, some normalized angle, and then we will have two kinds of neighborhoods, and both of them are within the 0 to 2p interval. So in this case, we have 2n continuous optimization problem, and the sequencing is for the TSP. Again, what we can do is decoupled approach. Now we can directly use TSPN, Euclidean TSPN, or just the TSP. We can transform the problem to GTSP. If we have the decoupled approach with sampling of the possible locations, and for each location, we will sample the headings. Our search graph is pretty much the same, but a bit more complex, but we can use the same techniques. And again, we can use self-computing and also unsupervised learning, which is unfortunately not covered in this talk because of time constraints, but that kind of heuristics. But regarding the heuristics, I like to show you this very simple, very straightforward local iterative. And as I mentioned, that we have 0 to 2p for all variables, and we can further normalize it to 0 to 1. And what we did here is that we treat each of this variable independently. So you can imagine that you have a sequence, so you iterate for the regions, and for each region you locally optimize by high climbing technique the heading and then the position, and you iterate over and over, which is very straightforward, but provides relatively good solution, and especially for the cases where the distances between the regions are more than 4 times the minimal turning radius. That's called D4. And there are some theoretical results that there is a convex optimization or local optimization is enough, basically because we don't have you don't need to use this C maneuver, if you remember, because that's the troublesome. However, we really like to achieve the same results as for the Dubin's traveling salesman problem or Dubin's Turing problem, kind of rubber bounds solution. We cannot use the Dubin's interval problem directly because we don't have points, we have regions. But we can generalize Dubin's interval problem to generalize Dubin's interval problem, and if we succeed with the solution of the generalized Dubin's interval problem, then we can use the same machinery for this Dubin's traveling salesman problem with neighborhoods. And Peter did it, and we identify 6 cases for optimal solution. The 7th case is kind of convex optimization, which is quick to compute. Just for information, what is the cost of, say, tuned implementation of finding optimal Dubin's maneuver? 0.4 microsecond. Dubin's interval problem a bit more demanding, and this generalized Dubin's interval problem, because it actually includes the Dubin's interval problem and Dubin's maneuvers as well, is more demanding. Regarding single point-to-point planning, 5 microseconds is nothing. However, within the context of Dubin's traveling salesman problem with neighborhoods with a given sequence, then it is more demanding. And here it is the application of the same schema that we have the splitting of the intervals, and we split the intervals on the neighborhood as these circles because we show the results for this. And we can refine and use here you can see nicely that is the feasible. It's not feasible solution, it's rubber bound because we compute the particular solution for this interval, like the neighborhood interval on this disk. And we can iterate, and what we can achieve is relative optimality gap, relatively nice. It is more demanding, and what we know, it is increasing proportionally to the number of locations, which is not surprising. We need to evaluate the sequence. But regarding the number of samples, it is less than, it's approximated less than k square. And if you consider that single solution of the Dubin's interval problem is like 1 microsecond, then solution of these 10 regions is more demanding. And so far we can actually achieve some or solving larger problems, but it is still relatively quickly growing. The results I show you are for a decoupled approach. So we bound the solution for a given sequence. But it is machinery that we can use to actually evaluate the sequences. And in this paper, what we try is to use these techniques to provide the efficient way how we can quickly assess the sequences and maybe quickly reject the sequences that are not promising. That is kind of building block that also provide us the way how we can assess the sequences, because if you have some possibility to estimate the solution quality for a particular sequence, then you just, let's say, you just need to generate enough sequences, enough good sequences, and evaluate them quickly. So far, we actually proceed with using these lower bounds to bound the search space in branch and bound techniques, and it is not yet finished, but it is very promising. So be tuned in a few months, maybe we will have the more practical results. It is actually working, but the complexity allows us like tens of sequences, tens of regions, tens of locations in this TSP, and can be solved in a reasonable time. But it is ensure optimal solutions. So now I will try to generalize the idea of Dubin's vehicle to variable speed. And it is motivated by the simple fact that even that for like this maneuver, we have this straight line segment, so we can accelerate with the vehicle here up to some limit and then decelerate. But there is another option, and that's is that the minimal turning radius is related to the vehicle velocity, and if we if the vehicle is moving at a higher speed, the turning radius is also higher, so it's probably the trajectory, the path is longer, but you can execute it in a faster way, and they can be a trade-off. So larger radius, faster speed, and we can optimize that. So we generalize the Dubin's path planning problem to multi-radius Dubin's path planning problem, that we assume that the initial turning radius can be different from the terminal turning radius. And what you can see in this animation is this scale is speed up comparing to the Dubin's vehicle, and it also includes acceleration on the straight line segments. And we can see that there is actually the trade-off, and we can benefit from that. So we put it to the TSP, and we call it a variable speed TSP. Maybe one more thing, that this can be solved in closed form solution. And what you can see here is that you can assume, okay, this is the minimal vehicle velocity, so it is the smallest turning radius, or you have maximum vehicle velocity and you need some larger radius. And what is the solution of this variable speed TSP? That's some trade-off between them. So you choose the turning radius. And how you can solve it, again, that's the continuous problem. What is the radius or velocity? You can sample that, and what you can see here is that the solution cost is decreasing with this computational time, and with for a higher number of samples. And definitely using just a single velocity, like one bound minimum or other bound the maximum, is not enough to actually speed up significantly. And if you will ask me what is the solver for this variable speed TSP, then we actually use variable neighborhood search. It's kind of meta heuristic. Now I will go back to the very first question, how it is in 3D. Simple answer is much more complicated because we don't have so nice results as for Dubin's. There is no known closed form solution, and everything needs to be solved in a numerical way. And we will discuss not very general 3D trajectory. We will discuss this 3D Dubin's path, where we have heading and we have the pitch angle that is limited. You can actually ask the motion constraint as a limited curvature. In general way, we can describe it as the curvature of the trajectory. And we can limit the pitch angle, which is actually the angle of attack going up, or the diving angle. So there are some limitations. So not the most general way how we can describe 3D paths, but still it is relatively difficult to solve regarding the existing approaches, what we can find in the literature, maybe are some other, and you can generally formulate the problem as a nonlinear optimization, put it to the solver and solve it. But what is remarkable in the literature is there exists a Dubin's airplane model, which follows the stated constraint, but they assume that if you climb and you reach some altitude, then you immediately change the pitch angle, which for many cases is sufficient approximation, but it doesn't have this smooth pitch angle. But it is quite fast to compute. Then there is the real-time dynamics, the Dubin's helix, let's say, algorithm. And what you can maybe observe here is that if we have locations that are relatively far enough with different altitudes, you can actually use the Dubin's path and then just change the angle of attack or dive angle. And what is the most difficult is that you have locations that are projected at the same location but at a different altitude, and what you need to do in that case is that you need to add some helix. So and how we approach that problem, 3D trajectory planning, we consider a decoupled approach. Now the decoupled approach is for splitting the 3D trajectory to horizontal and vertical paths. So we independently solve the paths for horizontal and for vertical planes, and then combine them. It seems to be quite fast. It also provides us good lower bounds. And if we compare to this RDDH with this helix, so this is the additional like spirals to reach the point, and the green one is our solution. It's not visible here. The solution costs are almost identical. That's our very, very teeny detail in the very small changes. But we assume that in some cases that this might be more suitable. What is the lower and upper bounds, or what are the? We just use the, for example, just for the vertical parts or the horizontal part. And the main benefit is that we can actually compute these lower bounds in the units of microseconds. And that's kind of way that we can future reject some possible sequences. But for now, we are speaking about point-to-point trajectory planning. And we follow this work and try to address also multi-core planning or multi-point paths. But first, we consider the previous approaches as a kind of initialization of nonlinear optimization. And we formulate it using direction vectors, which helps the solver a lot. But what we can still see that even that the improvement is relatively small, the failing rate is still high, and it is actually not very usable for multi-core trajectory planning. So for now, we are stuck here. So if you will ask me about 3D Dubin's traveling system problem, we are quite far from, let's say, optimal solution or a solution quality guarantee. However, from practical point of view, we can use this Dubin's airplane model, which has these abrupt changes in the pitch angle. It is quick to compute, and we can utilize it, and it is not from like computation point of view not that bad. Actually, it is quite usable. We can assume or generalize the regions. So the regions are 3D objects, and what you can observe here, and we can parameterize the waypoint of our 3D region that we like to visit as point on the surface. And for this type of regions, we have actually two variables. that describe the position of the waypoint on the boundary of the region. And if you remember the local iterative optimization, we did it also for 3D DTSPN using the Dubin's airplane model. And we have some sequence, Euclidean TSP sequence, and we optimize headings, and we optimize this alpha and beta variables that describe the position of the, and we can do that. And what, okay, that's, give me a second. Need to restart that. So what you can see here is the computation time is below 1 second. So it's perfectly working, let's say. Again, you can sample and solve it in a pure combinatorial way. Increasing number of samples will increase the solution quality, but it will be more demanding. Using this straightforward approach, we are somewhere here. Just this one. That's not bad. But unfortunately, we are not able to provide any like theoretical solution guarantee, only like the empirical evaluation. So far, this is still considered as an open problem. But for the very last two additional slides, this is future generalization. Again, not theoretical guarantees, but from practical point of view, we can consider multi-rotor vehicles as constrained only by maximum velocity and acceleration. So we need more general trajectory parameterization, and in our case, we choose Bezier curves. We need to estimate the travel time, so we need for any kind of trajectory, we need to estimate or define the velocity profile, and it's no longer length, it's time. And you can also mix multiple vehicles. So we are asking to visit set of locations by this example by 3 drones. And maybe you can see the drones here in the real deployment. And in this case, we use unsupervised learning technique, no theoretical guarantees, but what we can actually do, or what is my suggestion, how we can estimate that the solutions are probably not that bad, that we can take a look to the velocity and acceleration profiles, and if we see that the drones are like saturating the maximum velocity and maximum acceleration, that's probably okay. They use their capability as much as possible. And the very same setup can be put to this orienteering problem. So we can also increase the number of vehicles. So we will have team orienteering problem with curvature-constrained trajectories using these Bezier curves. And what I really like to highlight in this problem is that there is very important practical issue. So if you assume that these trajectories are actually found independently on the vehicles. If you are lucky, they don't mutually cross. But if you are not lucky, then the collision avoidance system that is implemented on the drones will somehow halt one of the drone that might be in the collision and perform this avoiding maneuver, which actually costs some time. And because you are now in the constrained time budget, the implementation of the optimal trajectory follower will try to reach the final location in time, because otherwise the drone will crash because of lack of energy. That means that the drone tries to reach the original plan, but you don't have the time, so you cut some of the waypoints and you don't reach the goal regions. You cannot score, you cannot visit them, so you cannot receive the profit, and completely crash the solution. So, and that's like motivation that you either need to think about coordination during the solution of this problem, or you need to replan quickly, and that's the demand for the planners. So that was like final teasers of the real deployments, and let me summarize the talk. That what I try to show you that Dubin's vehicle problem, or Dubin's vehicle in routing problems can be considered solved up to some point. And the point is that considering Dubin's traveling salesman problem, we have really nice results based on lower bounds. Regarding Dubin's traveling salesman problem with neighborhoods, we also have some very promising results. You can think about generalization of the velocity profiles. And there are kind of